Hey, so today we're going to talk about electrochemistry. Electrochemistry, first questions we have to ask ourselves is, first of all, what is electrochemistry? Electrochemistry over here is defined as the interaction between electricity and chemicals. In other words, it's asking ourselves the question of how we can go from using electricity to create chemicals and how we can use chemicals to create electricity. Before we dive in though, the type of reaction that's involved in this kind of conversion process is a reaction known as redox. Remember, redox was the simultaneous occurrence of reduction and oxidation. So with redox, what we remember one definition of redox was that redox was the gain or loss of electrons. And when chemicals gain or lose electrons, so let's say this is my chemical here, and it's lost an electron, this electron can go somewhere. So when this electron goes somewhere, and we have a whole bunch of electrons going a certain direction, we get what's known as a flow of charge. And remember, a flow of charge is going to be electricity. Electricity is basically a flow of charge from one place to another. So redox involves loss of electrons, which is a flow of charge. So electricity, when we have chemicals being used to create electricity, we have chemicals losing the electrons to produce that flow of charge. When we have electricity being used to create chemicals, we have electricity being pumped in one direction, so electrons are being pumped in one direction to create chemicals. So let's get an example in our head of what redox reactions actually are. So redox reactions, if we have a look over here, are going to be things like the rusting of a car, or when we use bleach. Obviously, when I Google image bleach, we get various definitions. Okay, so another example of redox reactions is something we'll have a look here. We can see Mark Rosengarten has got himself a strip of copper right here, okay, and he gets the copper and he puts it in front of the Bunsen burner and then turns up the heat, resulting in this oxidation reaction where the copper starts reacting like this. This is also another example of a redox reaction. And in this situation, as he'll later go and show you in the YouTube video, he has magnesium reacting with the oxygen to form magnesium oxide. So this is going to be a redox reaction as well. All right. So how does redox reactions pertain to the course that we need to look at? What we'll go through is the theory behind redox generally. So, and theory behind galvanic cells and electrolytic cells and electrochemistry. So remember back to our previous lesson, the definitions of oxidation and reduction. Okay. So remember that redox reactions involves simultaneous oxidation and simultaneous reduction. And oxidation is most commonly defined as the loss of electrons, whereas reduction is most commonly defined as the gain of electrons. And we recall this using the mnemonic oil rig. So we imagine that we've got ourselves a little bit of an oil rig like this. I can't draw. And this mnemonic basically stands for the fact that oxidation is loss and then reduction is gain. So remember, oxidation is loss of electrons, reduction is gain of electrons. So when we think about this, remember we have chemical A over here and chemical B over here. The notion is that if chemical A loses its electrons, the electrons must go somewhere and the electrons must then go to get chemical B. So chemical A is oxidized. So we say chemical A is oxidized and chemical B is reduced. Okay, there's a bit of confusing terminology here though, because sometimes the way that we'll describe these chemicals in redox is that we will call chemical A the reductant or the reducing agent. And the reason we call chemical A the reductant or the reducing agent is because it causes reduction in another chemical. So in this situation, we can argue that A causes reduction of B, causes B to gain electrons. So chemical A is oxidized, So it's losing its electrons, but it's called the reductant and the reducing agent. And likewise, chemical B will be called the oxidant or the oxidizing agent. All right, so always remember that the oxidant or reductant causes reduction or oxidation in another chemical, and itself is going to be oxidized or reduced like this. Okay. All right, so there's also a couple of other definitions of redox. So the other definitions that we have, are going to be oxidation is also the gain of oxygen, the loss of hydrogen, and think of hydrogen as being one proton in the middle and one electron. So when we lose a hydrogen, we lose the electron that the hydrogen has. And lastly, it's an increase in oxidation number. And of course, reduction will then be the opposite. It will be the loss of oxygen, the gain of hydrogen, and a decrease in oxidation number. Okay, so for example, the video we had before had magnesium plus oxygen forming magnesium oxide. So basically, sorry, it's supposed to be MgO like that, but we can see that magnesium gains the oxygen here, and we see here that magnesium goes from oxidation number of 0 to an oxidation number of -2. So sorry, what I meant was magnesium goes to oxidation number of +2, and because oxygen is always -2, magnesium goes from 0 to +2, and we can see that it's oxidized. Cool. Okay, so this comes to our discussion of a theory of how exactly is it that electrochemical reactions work. So electrochemical reactions are whether or not we get a redox reaction when we put two random chemicals together comes from this notion of Gibbs free energy. So we don't have to know anything about free energy or any equations or anything about it, but this is a good kind of background information so that we can better understand how the whole redox reaction stuff works. So the idea behind Gibbs free energy is that we have the energy of the reactants and the energy of the products, and the basic premise is that there has to be an energy difference, right? There has to be an energy difference in order for a reaction to spontaneously occur. Okay, so there has to be a difference in energy between the reactants and the products in order for the reaction to occur. Remember, this is different from the enthalpy idea we talked about. So instead, this is often known as entropy. But don't worry about this. This is a completely separate concept. But let's have a look over here at an example. An example is this. The example is that I have a jar of water, and inside the jar of water, what I'm going to do is I'm going to put in a bar of zinc metal. Okay, so this is zinc solid metal, and the zinc metal is inside this jar of water. Okay, and this is just H2O. And just for our purposes and for our information, what we can do is we can remember that water is going to be relatively bad at accepting electrons, and zinc metal is going to be relatively good at donating electrons. Okay, so it's good at donating electrons, and water is bad at accepting electrons. So what happens when we have when we stick this bunch of zinc metal into the water? So when we do this, right, what ends up happening is this. What ends up happening is that over here, zinc metal really likes giving away water. So let's say we take this over here and we zoom in a little bit. Okay, so over here on one side of the jar we have our zinc metal, and over here we have our water. So let's just imagine that this whole thing here is like immersed in water. Okay, so what will happen with the zinc is that the zinc when it's stuck into water, it will immediately donate an electron. Okay, so what we get is we get zinc immediately donating electrons. So the reaction that occurs is going to be zinc solid becoming zinc 2 plus 2 electrons. Okay, so the zinc will become a zinc 2 plus ion, and it will kind of like go from zinc solid here to a zinc 2 plus ion, which will be dissolved in the water. But at the same time, what happens is that there is a buildup of electrons and energy here. Okay, so we might have like 1 or 2 zinc ions go into the solution, but when that happens, electrons build up over here. Okay, so we can then ask ourselves, what happens with this idea of Gibbs free energy? So very basically, what the idea was is this: at the very start, we had like let's say we had high energy of the reactants. Right? So don't confuse this with enthalpy. This is a completely different concept known as free energy. And we had low energy of the products. Okay, well, let's just, for example, say that, right? But what happened was when I stuck the zinc, this is before, okay, when I stuck the zinc into the water, though, what happened? The zinc 2 plus ions go into the solution, but the electrons cannot be carried by water. They are only can be carried by a solid metal. So the electrons stay in the zinc, and there's a buildup of negative charge in the zinc there. So initially what happened was that there was a difference between the energy of the reactants and the Gibbs free energy of the products. But we can conceptualize this as the moment the zinc goes into the water, there's a buildup of electrons because the zinc gives away its it becomes zinc 2 plus ion, and it like quote unquote loses its electrons and leaves them inside this metal here. But the buildup of electrons results in a buildup of energy in this kind of like product state. So what happens is that now, if there's a buildup of electrons here, there's a buildup of energy, and there's all of a sudden no difference in energy levels between the reactants and the products. And remember, we said at the very start, if there's no difference in energy levels between the energy, the products and the reactants, then the reaction will not occur. So what happens is that sometimes we stick a metal or one chemical into another chemical and no reaction occurs. And this is the reason why, because of this lack of Gibbs free energy. However, what happens is this. Let's say, for example, what we do is we put the zinc this time into hydrochloric acid. So we get the zinc over here, and we stick this zinc into hydrochloric acid this time. So this is going to be HCl. Now, if we think about zinc and hydrochloric acid, remember zinc is really good at donating electrons. So it donates electrons or loses its electrons. And HCl is, this time compared to water, is better at accepting electrons. So it likes accepting and taking electrons. Okay, so this time when I stick the zinc into the HCl, what is it that we end up seeing? Okay, so what we end up seeing is going to be this. Okay, so let's say this is the zinc here, and this is the HCl here. Okay, so we know that the zinc is going to be donating its electrons. So the zinc jumps into the HCl and it loses its electrons. So it becomes zinc 2 plus. This is just the spontaneous process that occurs. The zinc 2 plus ion stays in the solution, and the electrons are left behind in the zinc. Okay, so we have the same situation as occurring before. However, this time HCl is really good at accepting electrons. So what really happens is that HCl splits up into H plus and Cl minus. And what happens is that some H plus will be attached to the surface of the zinc. Okay. So what happens is that H plus is attached to the surface of the zinc. And when this occurs, H plus is good at accepting electrons. So the H plus, right, will take the electrons and become hydrogen gas in this redox reaction. So the electrons over here will be taken away from the zinc into the hydrogen ions, and the H plus will then be like expelled or eliminated as hydrogen gas as per this redox reaction right here. So what does that mean for the zinc? That means that the moment the zinc goes in to the solution and gets this zinc, becomes a zinc 2 plus ion and leaves the electron here, the electrons don't stay there. Instead, the electrons themselves will be removed from the zinc by the hydrogen ions. So what does that mean in terms of the Gibbs free energy? In terms of the Gibbs free energy, it means that we have a high level of, so let's say this is the reactants and these are the products. So what happens is that since the electrons are being taken away by the hydrogen, we get a low energy, let's think of it like a low energy state in the zinc and like a high energy state out here. So we get a energy difference. The energy difference is maintained. So if there's an energy difference, that means the reaction is going to occur spontaneously. And what happens is that the zinc is slowly eaten away by the hydrochloric acid. But you can think of it as the hydrochloric acid eating away the zinc, but you can also think of it as zinc having a natural tendency to dissolve itself, right? And that the hydrogen ions just allow and facilitate this process from occurring. So now that we have this idea, let's have a look at the next notion. The next notion is going to be, how do we harness this kind of reaction to make electricity? Before we go through this notion, let's just think about what exactly is happening here. What exactly is happening over here when we look back at the zinc? Let's just get this. Okay, so what exactly is happening here is that we have the zinc metal in direct contact with the HCl. So we know that the reaction that the zinc is having is going to be, zinc becomes zinc 2 plus and 2 electrons, and the HCl is going to be 2H plus, is gaining the electrons, and then that's becoming hydrogen gas. So remember that zinc loses its electron. This is going to be, oxidation. And hydrogen ions are gaining electrons. This is going to be our reduction. Okay, so what's the deal here? We see that oxidation and reduction here are occurring at the same place. So we call this idea, right? We'll call this notion of what's occurring here as a direct chemical redox, right? Why? Because we get reduction and oxidation occurring directly between the chemicals. So this is what's occurring here. So the question then becomes, what happens in electrochemistry? What happens in electrochemistry is that what really happens is we just simply separate the oxidation and the reduction reactions. That's all that happens, okay? So in electrochemistry, what we'll do is we'll create what's known as a half cell, right? Where we put the thing that gets oxidized, or one thing that gets oxidized reduced. So in this example, we'll put the zinc here, and one thing that doesn't get oxidized or reduced. So, and the other thing that gets reduced or oxidized. So in this example, we had zinc getting oxidized, so zinc lost its electrons, and then we have the hydrogen ions, so H plus ions, in the solution here, and this thing here is going to get reduced. So on one side, we have our oxidation reaction, and on the other side, we have our reduction reaction. So they're separated by space. That's the thing that differentiates electrochemical from just normal chemical redox. So what happens here? We put the zinc solid into a solution, okay? And the zinc solid, as we know, likes to become zinc 2 plus. And remember that the electrons themselves are stuck in the zinc. So what happens is that we will put a wire in between the two of the things. So we put a wire between the zinc solid and the hydrogen ions, right? And there'll be another electrode here, which is just a block of metal that facilitates the transfer of electrons between the solid state and liquid state. Okay, so zinc solid is over here. Cool. And what happens is that we will put, we'll put the zinc into water and it becomes zinc 2 plus ions, and the electrons stay here. Normally, if this was just by itself and isolated, the electrons will build up and there'd be a buildup of charge and the reaction would stop occurring. However, what happens is that we connect this zinc block via a wire to this inert and like electrode, and that electrode is submerged in the H+. So what happens is that we know that H+ likes grabbing electrons. So instead of the electrons, when they build up in zinc, they will be built up in this entire circuit here, right? And they'll go all the way to the other side in this other jar, and where the electrons will then be transferred to the hydrogen ions that are inside the solution. Okay, so what happens is we have a division between the oxidation and the reduction, and this is the basis of electrochemistry. Okay, so what we will do here is we will have an examination of a basic cell. So we'll have an examination of a basic cell, whoops, and over here, and this cell is known as the Daniell cell. The reason why we look at the Daniell cell is because it's a common teaching cell that we use to talk about some of the principles that are involved in electrochemistry. Okay, so when we draw up this cell, what we have here is we have a bunch of zinc solid and we have a bunch of copper solid here. Okay, and the copper solid is immersed in a solution of copper 2+ ions, and zinc solid is in zinc 2+ ions. We also have ourselves a wire that connects between the zinc and the copper. Okay, remember that before we mentioned that the electrons would flow from one side to the other. So what we'll do is we can put something in the middle of this connected to the circuit. So let's say I'll put a light bulb there. So this is my blue light bulb. Okay, and in between the bottom we also have another thing. So between the two cells also is another thing in the middle, which we'll talk about in a moment. Okay, so with this situation, let's first of all examine what's happening. Via one process or another, we will have to find out which one of the two chemicals likes to give away electrons more and which one of the two chemicals likes to receive electrons more. That's what we have to do. So when we do that, let's we'll have other ways of working it out, but at this point in time, what we will do is we'll just simply say that zinc in this situation preferentially gives away its electrons, and copper 2+ ions, so be very careful, these are the aqueous copper 2+ ions inside the solution, not the copper solid that is the electrode here, okay, or the block of metal here. It's the copper 2+ ions that accept the electrons, not the copper solid, but the copper 2+ ions, and that becomes copper solid afterwards here. So when we look at these two reactions, the first question is, which chemical gains electrons, which chemical loses electrons? And we'll look at this, we'll look at how to do this in a moment. The second question then becomes the second question then becomes what are the reactions? Okay, so we've answered that question by looking at here at these two reactions here. Okay, the reactions will also tell you which one is going to be oxidation and which one is going to be reduction. Okay, so we can see over in the left side of the picture, over here we are going to have the loss of electrons, so this is going to be oxidation, and on the right side of the picture we have the gain of electrons, so we're going to be called reduction. Okay, so oxidation and reduction, there's a new mnemonic that I want you to remember, and this new mnemonic here is called an oil rig cat. Okay, so the idea is you think of a kitty, and the kitty is standing on top of a massive oil rig in the middle of the sea. Okay, so that's a cat that's on an oil rig. And why do we care about this? Because the place where oxidation occurs is known as the anode. and the place where reduction occurs is known as the cathode. Okay, so whoops, that should be pointing over here. So the point is that the anode is where oxidation occurs and the cathode is where reduction occurs. Okay, so when we come back to this situation over here, we see that oxidation occurs at the zinc electrode. So this place here is going to be known as what? An oil rig cat. So anode oxidation. So this thing here is known as the anode, whereas over here, this thing thus is going to be known as the what? Cathode. Very, very important to get very familiar with this. Okay, so anode and cathode. The next idea is going to be this. All right, let's have a look. So what we have here is we have the this is going to be zinc becoming zinc 2 plus 2 electrons. So we know that this is going to be the anode, and this is going to be copper 2 plus 2 electrons forming copper solid, and this is thus going to be the cathode. Right? Cathode. Cool. So if we have a look at the way that the cell is set up, we see that there's a solid electrode here, and there is a an aqueous electrolyte over here. So this thing here is known as the electrode, and this thing here, the solution that the electrode is immersed in or is in contact with, is known as the electrolyte. Okay, so I need you to have an idea of what these mean. Electrode is simply a medium between the solid state and a liquid state, right? So we see that this is a metal. This block here is supposed to be a metal, and this solution here is supposed to be a liquid. So an electrode is a medium that allows the conduction of electricity between the solid state and the liquid state. Okay, and we remember that beforehand we had a situation where we had like zinc here, and we had like hydrogen ions here. Okay, so you can think of it, right? This isn't exactly right, but you can think of it as when zinc donates its electrons. So zinc here would have like become zinc 2 plus, and there's electrons left in the solid. When the electrons then go and jump to the hydrogen, we see like there's think of it as like a transfer of electricity from the solid state to the liquid state, because the hydrogens are like in the liquid or in the aqueous solution. So that's what an electrode, the purpose of an electrode is, to transfer electricity or charge between the solid state and the liquid state. Okay, so then we have an electrolyte. Electrolyte is simply a solution that has ions in it. So think of Gatorade. Gatorade, you'll see the advertisements, they say we have essential ions like magnesium, like sodium, like potassium, etc. It just means that it's water with a bunch of ions dissolved in it. And in this situation, we see that there's zinc 2 plus ions dissolved in this solution. So this is an electrolyte here, and we have a copper 2 plus ion dissolved in this solution. So this is also an electrolyte here. And the last notion to add onto this is what? Is that the electrolyte here is the electrolyte of the anode. So remember, just think back to our mnemonic, an oil rig cat. Okay, so the anode is the electrode or the place where oxidation occurs. Additionally, the electrolyte in which oxidation occurs is known as the anolyte. Okay, so the anolyte is the electrolyte where oxidation occurs, and conversely, the electrolyte where reduction occurs is going to be the catholyte. Okay, so what I want you to, so the catholyte here. Okay, so let's have a look. Cool. So what we've got here is we've got this thing here, right? So remember, zinc here is going to be oxidize. So this is going to be the anode, this is going to be the analyte, this is thus the cathode and the catholyte. Okay, so what we want to be able to do, the third step of what we want to be able to do, so before, remember the first step was think about which chemical gives away electrons, which chemical gains electrons. Second step, determine what the anode and cathode are, where reduction and oxidation occurs, and what the reactions are. Third kind of notion that you want to think about is just to get an idea of how electrons and ions are flowing in the solution. Okay, so third step is think about what is going on in this cell. Okay, so we start by looking at the reactions. Zinc converted to zinc 2+ plus 2 electrons. So over here, we know that zinc is going from a solid state into the zinc 2+ state. Okay, so it's going to become an ion, right? And it's going to lose electrons. So electrons are going to be left in here. Okay, as this occurs, it must make sense that zinc solid is getting used up. So what will happen is that this zinc here is slowly going to be corroded away. Okay, and over here, the concentration of zinc 2+ is going to increase as time goes on, because more zinc 2+ is being produced and it's going to the solution. The electrons are here. Remember that the zinc is where oxidation occurs, so the loss of electrons here, and copper is where reduction occurs, so gain of electrons here. So it makes sense that the electrons are flowing from the zinc electrode towards the copper electrode. As the electrons flow, they can power the light bulb, and in chem terminology, this light bulb is called a load. Okay, so it flows over to the copper. The copper solid itself doesn't do anything to the electrons. It just carries the electrons along until it can come into the solution. Inside the solution over here, remember it's copper 2+ ions that really love the electrons. So what will happen is that there'll be a bunch of copper 2+ ions stuck to the surface of the electrode, and then the electrons will be absorbed into the copper 2+. So the copper 2+ here will gain the electrons and will become copper solid. So what happens when it becomes copper solid? Well, we'll get a deposition of copper solid around the surface of the electrons like that. Okay, and that's basically what happens.